The fabric of color, azo dyes and actions. We're going to be talking about dye chemistry and different types of dyes in this presentation. Why should we focus on dyes? Dyes transform key industries. Dyes significantly impact food and textiles, offering brighter colors and the potential for safer food additives. A lot of the food that we eat nowadays contains artificial colors such as like red 40 and blue 1. If you have noticed ever on like the back of Gatorade products or Kool-Aid specifically, you'll see a whole like slew of different artificial food coloring that is used in these products, and we can design different types of dyes to hopefully be safer for food consumption. We can also advance environmental goals. This is the main like research for a bunch of dyes nowadays, because a lot of dyes that we developed in the past were specifically carcinogenic and caused cancer, which is not good if we're putting this stuff on clothes. We want to encourage and develop and adopt more sustainable dye production methods for greener impact. A really cool technology that's being observed today is CO2 dyeing, which prevents a lot of the harmful chemicals that are typically used in dyeing process. And dyes also are used a lot in technological processes such as like OLED displays, and also my favorite, which is film and instant photography. First, we have to talk about light, what light is, and how light allows us to see. So light is a fundamental form of energy. It behaves as both a wave and a particle. We only are able to see a certain spectrum of light. This spectrum is called the visible spectrum. Dyes and color perception. Dyes contain molecules which selectively absorb specific wavelengths within the visible spectrum. This absorption causes electrons in the dye molecule to jump up to a higher energy state. The color we see corresponds to the wavelengths of light that are not absorbed by the dye. This is the visual spectrum of light. There is a whole bunch of just like stuff that you can look at. We see a very short range of this energy, but there's a whole bunch of like wave energy, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Typically, the longer the wavelength is in the visible light spectrum, we'll see red, orange, and yellow colors. The shorter the wavelength, we'll see more of the blue, violet, and cyan colors. This presentation is going to focus more on azo dyes, because azo dyes are a huge category of synthetic dyes. And it's really interesting because azo dyes are mostly synthetic. There are a couple examples of naturally occurring azo dyes, but that is a very rare instance. There's only like one or two that we're able to find. I don't remember what they were, but I know it's very rare. But azo dyes are a type of synthetic organic dye that is characterized by the presence of one or more azo groups. These are nitrogen double bonded to another nitrogen. They act as the primary chromophore. These azo groups typically link two or more aromatic ring systems, such as benzene rings or nalphene rings. I'll show you what those are in the next slide. We are going to focus on these dyes because they are the largest and most versatile synthetic dyes. They account for half of all commercial dyes produced. They can be made into almost every color and are widely used in textiles, food coloring, and also pH indicators. And a fun fact that I found is around 700,000 tons of azo dyes are produced per year, and this is coming from the National Institute of Health. This is red 40. This is a very common azo dye that it can be found in a lot of food stuff. Like if you look at Takis, they have red dye. If you look at Gatorade, they have red dye. If you look at Kool-Aid, they have red dye. A lot of stuff has red dye in it. You can see those benzene rings. Those are the like hexagon looking things. You also have that N double bonded to another N, which is that double bonded nitrogen group. You also have the nalphene ring, which is those two ring junctures that are bonded together. You also have some sulfonic acid groups. Those help it dissolve in water. And most times these food colorings come in salt forms, which allow it to be able to dissolve into liquids a lot easier. And this allows us to be able to dye a lot of stuff that contains water. We're going to look more about how diffusion and color production and color chemistry in dyes. We're going to start with diffusion, and then we're going to move on to how dyes produce color, and then we're going to look at specific types of dyes and like dye categories. We're first going to talk about diffusion. When we talk about diffusion, this is the process by which dye molecules move from a higher concentration dye bath to a lower concentration substrate, which is typically the fabric that we're using. This type of dye significantly impacts how easily diffusion happens for a specific fabric. When we talk about this dye moving, typically dyes are dyed in a large vat of dye. This is called a dye vat. And typically when you submerge a fabric into that dye vat, it will absorb the color, the dye, which then gives the fabric the color. And then when we talk about how dyes produce color or reflect color, this is due to how the molecule can absorb certain wavelengths of visible light and reflect and transmit the remaining wavelength, which our eyes pick up as color. So what are some key factors in diffusion? The molecule size, that affects diffusion. Polarity and solubility also affect diffusion. Typically, you want to match the dye to the type of fabric that you're using. We'll look more at that later. You also have ionic charge. These play a role in how the dye and fiber are attracted to each other. And then you also have affinity, which is the strength of the dye-fiber interaction. So how does molecular size play a part? Typically, the more smaller and more compact the dye molecules are, they will generally diffuse and penetrate fibers more easily. The larger and bulkier dye molecules are, they generally diffuse more slowly and may struggle to enter tightly packed fiber structures. Now we're going to look at polarity and solubility. The general rule of solubility is that like dissolves like. Typically, dyes diffuse best into fibers with a similar chemical structure to theirs. There are certain types of dyes, hydrophilic and also hydrophobic. Hydrophilic dyes, these are water-loving. This is what we talk about when we talk about food dyes because they dissolve in water very easily. Generally, these diffuse effectively into hydrophilic fibers like cotton, wool, silk, rayon, and nylon. When these absorb water, they swell, and then that dye is able to penetrate those fibers, pores. When we talk about hydrophobic dyes, these are water-hating. They do not like water. They do not dissolve into water easily. These are used for polyester and acetate fibers, which require high heat or carriers that help diffuse them into the fabric. The role of ionic charge, there are different types of ionic charges. You have catatonic, which are positively charged, anionic, negatively charged, and disperse, which are neutrally charged. Anionic dyes, typically they're acid, direct, or reactive dyes. Because they carry a negative charge, they are attracted to positive sites within fibers like wool, silk, and nylon. Especially under acidic conditions, diffusion depends on pH and available sites of bonding. Then you have cationic dyes, which are normally basic dyes. They carry a positive charge and are attracted to negative sites within fibers like acrylic. And then you also have non-ionic dyes. These are dispersed dyes. They typically carry no charge. Diffusion relies on weak intermolecular forces and concentration gradient, especially in hydrophobic fibers. Affinity. How does this affect diffusion? The natural attraction between a dye and a fiber influences absorption, which is the initial binding to the surface, but very high affinity can sometimes slow down the rate of diffusion deep into the fabric core. Dyes and light absorption. Now we're going to talk more about how these dye molecules absorb and reflect light. Dyes appear colored because the molecule is able to selectively absorb certain wavelengths of visible light and reflect the remaining wavelengths. These reflected light waves are what our eyes perceive as color. So how does the structure play a part? And we're also going to look at different functional groups. These molecules contain chromophores, which are what give the molecule the ability to absorb light waves. These molecules also typically contain a conjugated system. These are networks of alternating single and double bonds like benzene and naphthalene rings. This allows electrons in these conjugated systems to be able to resonate and absorb specific amounts of light energy, and then they jump to higher energy levels, and then when they become relaxed, they jump back down, and then this is the light that we see. This conjugation determines which wavelengths are absorbed, which defines what color the molecules will absorb. Typically, longer conjugation generally absorbs longer wavelengths. This is an example of like the conjugated systems. You can see you have like a red dye here, and then you have a blue dye there. You can see how much bigger the blue dye is than the red dye. So we're going to continue this idea. We also have groups called oxychromes. These help the color. These are functional groups that are attached to the chromophore. These modify the molecule's color producing ability. They do not produce color on their own, but instead help to shift the color through resonance. Some common examples are hydroxyl groups, amino groups, carboxyl groups, sulfonic acid groups, as we saw on red dye, and nitro and chloral groups. These can also help to make the dye more or less soluble in water, such as sulfonic groups and carboxyl groups. These help molecules dissolve into water better. These also help to provide bonding sites for the dye to be able to bond to the fabric substrate that we are trying to dye. So now we're going to dive more into different classifications for dyes and how they interact with different fabrics. We're generally going to focus on these types of dyes here because there are a lot of different types of dyes, but these are the dyes that are typically used for fabrics. The dyes that we're going to focus on are acid dyes, basic dyes, direct dyes, insoluble dyes, vat dyes, fabric reactive dyes, dispersed dyes, and moderate dyes. Insoluble dyes. These dyes are formed directly on the fabric. They are not pre-dissolved in a solution. Instead, two chemicals react on the fabric to create the insoluble color. This type of reaction is called coupling. The final dye doesn't dissolve in water. Instead, it sits mostly on the surface of the fabric. This is mainly used for cotton and silk, and sometimes is used for nylon and polyester. Often these produce bright colors, but a downside is that they have high fastness, which is the color does not last well through washing or rubbing. This is an example of an insoluble dye called indigo. This is used in vat dyeing typically, but you can see the structure of it there, and then you can also see the powdered version there too. It's a very nice blue color. It's typically used for jeans. Then we're going to move on to vat dyes. These dyes begin as water insoluble pigments. They cannot directly dye the fabric in this form. The way that we dye this fabric is a process called vatting. This is when they are reduced to become soluble. This is often done by sodium hydrosulfite, the reducing agent, and an alkali, typically sodium hydroxide. This allows it to be soluble. This is called the leucoform, and in this state, they can be absorbed by the fabric. After the dye is on the fabric, we can then oxidize it, which then converts it back to the original insoluble form. Now, this insoluble dye is trapped inside the fibers, and then this allows us to have excellent wash fastness, which is really good for clothes. And then this is typically used on fibers like cotton and linen. This is an example of that dye, endothrone. You have its color there in its powdered form, and then you also have what its chemical structure looks like. Then we're going to move on to fiber or fabric reactive dyes. These dyes have a special reactive group in their structure. This group allows the dye to chemically react directly with the fabric fibers, and then this allows them to form a strong covalent bond. Because the dye is chemically bound to the fabric, they tend to have excellent fastness. And then common fabrics that we use this dye on are cotton, and then it also has been used for wool and silk. This is an example of a reactive dye, bright turquoise dye. It's a very bright blue color. You can see its powdered form there, and then you can also see its chemical structure too. Then we're going to talk about dispersed dyes. These dyes have very low solubility in water. Firstly, they're ground into extremely fine particles. Then these particles are dispersed in water. This is usually with help from a dispersing agent, but they might look like they're truly dissolved in water, but they're not. They're just floating in there. They are typically designed for hydrophobic fibers, which are typically synthetic fibers like polyester, nylon, and acetate. This is an example of a dispersed dye, dispersed red 1. There's its powdered form and also what its chemical structure looks like. I just wanted to point out too, you can also see that it is a type of azo dye due to that nitrogen double bonded to another nitrogen. And you can also see its conjugated system with those benzene rings, and then also those oxochromes that are helping produce that red color. Then we're going to look at moderant dyes. These dyes don't bond directly to the fabric on their own. They instead use a moderant, which acts similarly to a binding agent. Usually this moderant is applied to the fabric and sticks to it. Then the dyes are applied and they attach firmly to the moderant. Common fabrics that we use this on are natural fibers like wood, and it also has historically been used on cotton and silk. This is an example of a moderant dye, alizarin. It's a red color. You can see it on the powder form there, and then you can also see its chemical structure there too. So what are some practical applications of dyes? One of the practical applications we're going to look at is how they were used in film and also instant film technology. My experiment investigates the role of dyes in film and instant photography. This topic merged my passion for photography, which evolved from digital formats to now analog formats such as film and also instant film. This was because I really like chemistry, and I also find dye chemistry really cool, and it kind of merged both of those topics: photography, dye chemistry, and also chemistry in general. It's a really neat and interesting subject if you ever have free time to look it up. I will warn you, it is a lot of organic chemistry, and it also is just a lot of chemistry in general. So if that stuff scares you, then stay away from dye chemistry. While exploring dyes, I learned that a lot of the mechanisms behind older photographic techniques and methods was actually dye chemistry. We'll look more about this, and a lot of this too involves azo dyes. And if you guys are okay with it, I brought my Instax camera with me, and if Dr. Piot is also okay with it, we can take a photo at the end of my video to demonstrate this technology. So first we're going to talk about the mechanics of instant cameras. This is how the camera actually works. So the operation of an instant camera relies on several key mechanical components. First, you have the lens that focuses the light onto an internal photosensitive film sheet. And then you have the shutter, which precisely controls the duration of this light exposure. And then after exposure, the film is typically ejected, and as it's ejected, it's pushed through rollers. These mechanical rollers help to apply the developer evenly in a thin sheet along the film, and then this starts the photoreactive dye developing process. You can see that the pressure from those rollers ruptures a little pod, like I said, and then this mechanical spreading initiates all of the chemistry in film, which is really cool. This is for instant film. There's a whole nother chemistry for like film. I'm not diving into that, but most of it relies on halide chemistry, like silver halides. Typically, when you expose a silver halide to light, it will become a silver molecule, and that silver molecule is what gives that black and white color that you see in original like film. So what is the chemistry of instant film? Instant film relies a lot on complex chemistry. I'm not going to go over all of the chemistry because it is way too long and it's also way too complex. Typically, it involves photochemistry, which are light reactions and oxidation reduction processes. I'm going to give more of a basic overview of it. So first, you expose the film. This activates the silver halide crystals in the emulsion layer. Then you develop it. So after the exposure, that it goes through the rollers. Those rollers like squeeze out the developer in that little pod, and this starts that chemistry. That packet typically includes developers and also dye molecules. And then you form the image. In the areas that were exposed to light, the activated silver halides react with the developer. This reaction immobilizes the nearby dye molecules, preventing them from transferring in unexposed areas. The dyes are free to migrate to the image receiving layer, and then this creates the colors as you see. Then, when we form the image, it's not super stable, So then it has to go through a stabilization process. There's a whole bunch of layers. There's this thing called a timing layer, which after a specific time, it will release an acidic layer that eventually neutralizes to an alkaline reagents, and then this also stops the development and also stabilizes the final image. There's a whole lot of like books and cool articles on old chemistry of like film and also instant technology. If you like organic chemistry, I would highly recommend reading it. It is really interesting to me. I will also pass around like a dissected film sample of like an instant film, like a Fuji instant mini film. It's kind of interesting, but also not super interesting because a lot of the layers in instant film are very thin, so you can't really separate them very well. But the article that I found, or the paper that I found, gave a really nice diagram of all the different layers that you can see on the left there. You have like your blue layer, you have your yellow layer, you have your magenta layer, and all of these help form the image that you can see. That comes from a book on instant photography. There's the ISBN if you're interested in it. These are all of my sources. There are a whole bunch of cool books if you're into organic chemistry. And thank you for watching my presentation, and I hope you learned something and also